Hello guys, it's Jesse Polymath project with Jessio, and like I'm always here when I see something that hits my radar. And right now I want us to talk about a particular problem. And yes, that being said, it's been a while and I always like to do this all the time, off and on, but work doesn't give me the chance to. But that's not what we're about. So let's solve this problem. This is a wide question from 2016, and a few of us who might not know what's going on here would be baffled about this question, but trust me, it's pretty easy. An RLC series circuit consists of a 100 ohms resistor, a 0.05 Henry inductor, and a 25 microfarad capacitor. A 220 volts and 50 hertz mains voltage supply is applied across the circuit. Calculate the impedance. You have to understand the relationship here. We have inductors, we have capacitors, but we don't just need that. We have to convert it to some sort of certain term which helps us achieve what we want. An inductor, we all know, is not meant to oppose the flow of current. It serves as some sort of electromagnetic system that induces either voltage, current, or whatever signal it is required to. While capacitors store charges, that's the idea of it. Now, when this component starts to oppose currents, especially let's say an inductor, it becomes an inductive reactance. For a capacitor, if it starts to oppose the flow of current, it becomes a capacitive reactance. Now, there is a formula to changing or obtaining inductive reactance. Let's call inductive reactance XL. Okay, first let's highlight our solution. So XL is given by 2 pi FL, where we already know that 2 and pi are constants. F here is the frequency, while L is the inductance. Then for XC, that should be about 1 over 2 pi FC. Now, using these terms, we can convert our inductors, inductance into inductive reactance, and even capacitance into capacitive reactance. Now, let's hit at it. So 2 times 3.14 times, our frequency here is 50 hertz. Permit me, my writing is somewhat bad. It's been a while I did this. So, okay. Okay, so that would be 50 then times our inductance, which is 0.05. This would give us an amount of 2 times 3.14 times 50 times 0.05. That gives you about 15.7. So we have 15.7 here, and it becomes ohms. The moment capacitance, if the moment inductance is changed into inductive reactance, it is now measured in ohms. So now we have this 1 all over 2 times 3.14 times 50 times 25 times 10 raised to power minus 6. We all know how to work with our submultiples. The fact that we have 25 microfarads, micro there is a submultiple for 10 raised to the power of minus 6, definitely. So that's what we plugged in here, 25 times 10 raised to the power of minus 6. I don't want to start telling you how this works, but I like to make my 10 raised to the power minus 6 go up to the as numerator. And the principle for that is that this one here gets to be multiplied by 10 to the power of 0. And we know that one index notation of the same base are dividing, the powers are subtracted. So we have 0 minus minus 6, making it 10 raised to the power of positive 6. And that entails 1 times 10 raised to the power of 6 all over 2 times 3.14 times 50 times 25. So that would exactly give us 2 times 3.14 times 50 times 25. That would give me about 7,850. So 7,850 all over 10 raised to the power of 6. So that's about 1 million. So 1 million divided by the answer we've gotten, and that would be about 127.39 ohms. Now that we have our inductive reactance and capacitive reactance, we can establish the relationship between all the resistive components. We all know that the relationship between XL, XC, and resistance is a graph like this, of which we have here to be XL, the positive side of Y, while the XC is the negative side of Y. So the resultant here happens to be what we call the impedance. This all the way boils down to the use of Pythagoras theorem, because here we obtain some sort of right-angled triangle, something like this. If you are to check the resultant, it's something like this, where we have the horizontal axis to be R, the hypotenuse to be Z, which is the impedance, while here happens to be XL, because we are getting the resultant for all reactances, XL minus XC. So that means the formula for impedance is going to be equal to all under the square root of R squared plus all in the bracket XL minus XC, all raised to the power of 2. So the next thing we're going to be talking about is how to resolve this. Let's resolve this. So we have plugging in values. Impedance would be equal to, our resistance here is 100 ohms, so 100 raised to the power of 2 plus all in the bracket. My XL here before now was 15.7, so we have 15.7. The thing is that the idea here is that it might boil down to something negative, but you don't have to worry. We are working with absolute values here. So, and even if we aren't working with absolute values, the square here nullifies it, nullifies the negativity, and we just have here about 10,000 plus, and here we have about 15.7 minus 127.39. That would give me, sorry about that, that would give me all in the bracket negative 111.69 all raised to the power of 2. So negative 111.69 whatever should be giving us something about, I'm adding everything up though. I'm adding everything up so that we can get answers. So I have here 22 So the square root of that would give you, we've finally found out z. The square root of that would give you, I feel like my ink is bleeding a lot and it makes my writing really bad. So we have here 150 ohms. So the resultant opposition is about 150 ohms. And then how do we handle the current? I mean, that's one of the basic things. You're going to be using the Ohm's law. Here, we're not working with I times resistance, the current times resistance. You are working with the current times any resistive component, which happens to be the impedance. So II using Ohm's law. Which entails we have something like V, potential difference across a metallic conductor, if every other condition is kept constant, is directly proportional to the current flowing through it. Well, closely it. Making I subject to the formula entails that you divide through by Z, of which I, being the current, is now equal to V divided by Z. So I think we're given the value of our resistance here, our voltage here, which happens to be 220. So current is always meant to be small. So we have 220 divided by 150. So 220 divided by 150. That gives me just about 1.47 amps. And we've just heard about it. So this is 2016 practical question and theoretical questions, all easily solved. So for things like this, the more you can always find me. You can always reach out. I'm always here to put you through problems like this in physics, further mathematics as well. And I hope to see you soon. Okay, and bye. All right. Okay, so reach out to me on the various platforms. These are special thanks to people who make my content creation work here very motivating and engaging. So see you soon. See you soon. See you soon. Bye.